Okay, in this video we're going to talk about hydration of alkynes. So just like in alkenes, alkynes can undergo acid-catalyzed hydration, and we get Markovnikov addition, where the OH gets added to the more substituted carbon. For alkynes, the reaction is slower than in alkenes, and so the reaction is usually catalyzed with mercury sulfate. In the reaction, so we start with our alkyne. We have sulfuric acid, which is the acid catalyst, and then we also have a mercury sulfate catalyst. And so we add the OH to the more substituted carbon from the alkene, but as we're going to talk about, the OH is actually an intermediate in this process, and what's called the enol, right? So when we name alkenes, it's En, and as we're going to see in the second semester, when we name alcohols, they end in OL. So when we have a double bond and an OH together like this, it's called an enol. But under acidic conditions, it turns out that the enol is not generally isolated, and it further reacts to form the ketone. And we'll talk about what that mechanism looks like as we go through the video. Now, I do want to go through the mechanism for the acid-catalyzed hydration of alkynes, but I won't ask you to reproduce this. So in the first step, one of the pi bonds attacks the mercury to give us this product. We then get a nucleophilic attack by the water. And then, as we've seen in a lot of mechanisms, we then have another water molecule that helps us with proton transfer to give us this intermediate. We then have another proton transfer step that gives us this intermediate. And we actually have a resonance structure where we can either have the positive charge here on the carbon, or the lone pair from the oxygen can come down to give us a double bond between the carbon and oxygen, moving the positive charge to the oxygen. And then in the final step to form our enol is we have the loss of this mercury ion. Although unlike other loss of leaving groups that we've seen, right, the mercury doesn't get the electrons. The electrons stay with our substrate. Okay, now as I mentioned earlier in the video, we usually aren't able to isolate the enol, and instead it undergoes a reaction called tautomerization. And in particular, this process is called Keto-Enol Tautomerization, where we actually have a equilibrium between the enol and the keto. Now, I said that you didn't have to know the mechanism on the previous slide. I would like you to be able to draw the mechanism for, in this case, the acid-catalyzed keto-enol tautomerization, and then later in the video we'll look at the base-catalyzed, and I do want you to be familiar with both of those mechanisms. So in this case, this is the acid-catalyzed tautomerization. So we have H3O+, we have our acid, and we start off with a proton transfer where the pi bond from the enol grabs the hydrogen. That gives us this carbocation intermediate, but it is resonance stabilized, and so we can move the lone pair from the oxygen down to give us the double bond between the carbon and the oxygen, which moves a positive charge to the oxygen. And then in the last step to form the ketone, if we have another water molecule come and deprotonate our intermediate, then that gives us the ketone. So I would like you to be familiar with this mechanism. So we start off with a proton transfer, then a second proton transfer to give us the ketone. Now, under some conditions, we can actually get the enol, but generally the equilibrium will favor the ketone. Okay, so we just saw in acid-catalyzed hydration that the OH would add to the more substituted carbon, and then we'd get the tautomerization to form the ketone. But again, that ketone, that double bond oxygen, is going to be on what was the more substituted carbon from our alkyne. Well, just like in alkenes, we can get anti-Markovnikov addition if we proceed with Hydroboration-Oxidation. And so in this case, right, we form the enol where the OH is on the less substituted carbon from the alkyne, and then we also get the tautomerization to form, in this case, the aldehyde. Right now, in this case, because we're under basic conditions, the tautomerization is actually base-catalyzed. And so let's take a look at that mechanism. Okay, so for the base-catalyzed tautomerization, we again start with a proton transfer, but in this case, rather than the enol stealing the proton from the acid, now our base is going to steal the proton from our enol. This results in the formation of an enolit ion, which is also resonance stabilized, and so we can have a lone pair from the oxygen move down, and then the double bond turns into a lone pair on the carbon atom. We then have a second proton transfer step where now our enolit ion steals a proton from a water to give us our final product, the aldehyde. Now it turns out if we use boron trihydride to do the hydroboration, we actually get two successive additions. And oftentimes that's not what we want. So to only get one addition, we often use a dialkyl borane. And so you'll see as our reagents, rather than BH3 when we do these reactions with alkynes, is you'll see one of these two as our reagents rather than the BH3. All right, so when we use these modified reagents, we get the desired aldehyde. So to sort of summarize things, if we do acid-catalyzed hydration with mercury sulfate as a catalyst, then we get a ketone. If we do hydroboration-oxidation, where rather than doing BH3, I have two alkyl groups, then we get the aldehyde, so we get the anti-Markovnikov addition.